Okay, can you hear me? Okay, great. Am I supposed to be? Okay. Right, so thank you. Thanks for asking me to give this series, and it was a pleasure. Right, so I'm talking about the Hodge state decomposition, but maybe I guess in the spirit of the previous lectures, I should say something about my experience at the Winter School. So I came here twice, once as a senior undergrad and once as a second-year grad student. And I have to say I was a pretty delinquent participant, so I was probably not the best model for the grad students here. But I do want to re-emphasize a point that Jared made, which is that I did meet a lot of my current colleagues here then as graduate students, so really take this opportunity to meet people. Okay, right, so I want to explain the Hodge state decomposition in this series of lectures, but I want to sort of slowly build up to it, and we're going to sort of do it using the machinery of perfectoid spaces. But in this first lecture, I really want to just explain what the statement is and how it sort of relates to other things that you might have heard about. So let me begin by actually talking about the Hodge decomposition, which is where the motivation comes from. Okay. Right, so this is a situation over the complex numbers, which was sort of more classical. And so let's say you have a smooth projective variety over the complex numbers. And then the theorem in this case, which is the Hodge decomposition, it sort of gives you a way of relating two very different cohomology theories associated to X. One is a topological invariant, which is its singular cohomology, and the other is sort of a more algebra-geometric invariant coming from coherent cohomology, things like the structure sheaf and differential forms and so on. And so the theorem is that there exists a natural isomorphism, let's say it goes from, so I'll write Xn for the associated analytic space, and X sin Q is its, so that's its p-adic cohomology or singular cohomology with Q coefficients, tensor up to C, looks like a direct sum over I plus J equals N of Hi of X, omega J of X over C. So the right-hand side is the objects one sort of encounters when reading Harshon, for example. And this is saying that there's this nice sort of connection between these two very different ways of viewing an algebraic variety, either as something defined by polynomial equations or as like a topological space where there's a good notion of loops and so on. And so the Hodge state decomposition is some kind of a p-adic version of the Hodge decomposition. But in order to convince you that this is actually kind of a very non-trivial thing, let me sort of do an example. So this example really is meant to illustrate why the Hodge decomposition is a really transcendental operation. It's not an algebraic thing, even though you could probably define both sides algebraically in some way. And so let's say X is an elliptic curve over C. So this means that you can write E or X as C mod a lattice lambda. And part of the Hodge state decomposition, so in the case of elliptic curves, the most interesting cohomology group to look at is H1. And in this case, the Hodge state decomposition says that H1 with Q coefficients decomposes into these two pieces. In particular, it gives you a very interesting map from differential forms on X into an injective map even. It's singular cohomology with Q coefficients, C coefficients. Okay, and so let's try to understand what this map looks like. So the left-hand side is something one can easily sort of figure out. So it's a one-dimensional vector space, and it has a generator, which I will label omega. It's the invariant differential form on the elliptic curve. It's dx over y in suitable presentation. And the right-hand side, one can also understand in terms of this lattice. So H1 with Q coefficients, or H1 with anything, is always homomorphisms from the fundamental group into the thing. So in this case, we're looking at homomorphisms from the fundamental group of E into C, or into Q tensored up with C. But that's the same as just homs from lambda, because lambda is the fundamental group of the elliptic curve, into C. So it's the C linear dual of the lattice lambda. It's a two-dimensional vector space. Oh, sorry. Am I speaking too loud? Write bigger. Okay, thanks. So it's a two-dimensional vector, but sorry, on that. Is my voice okay, or is it hurting your ears? Okay, great, thanks. All right, so how does this map work? So it sends a form omega to a functional on the lattice. So what is the, you can think of an element of the lattice as a loop that goes around the elliptic curve. And then what the function is doing is that it's saying to pair omega against gamma, you integrate one over the other. So the function is gamma goes to the integral of omega over gamma. And so in this way, you pick up the periods of your elliptic curve via this isomorphism over here. So the point is that this is highly transcendental. And what you're trying to do is a p-adic version of this. Okay. I wanted to record one corollary before I talk about the p-adic version. So the corollary is as follows. So I underline natural in the statement of the Hodge decomposition. And so what this means is that it is natural with respect to morphisms between algebraic varieties. So in particular, if you're in the situation where you have a map, F from X to Y, of smooth projective varieties, and you know for some reason that the pullback on the nth cohomology group with Q coefficients is an isomorphism for some n, so this is F upper star. Then it's an isomorphism also with C coefficients, and the naturality tells you that the direct summands actually have to line up as well. So in particular, what it says is that HI of X, omega J of X, maps isomorphically to HI of Y. Well, let me go the map in the other direction. HI of Y, omega J of Y, Y F upper star. And this is for I plus J equals N. So the summands that show up in this particular cohomology group also have to match up. And this is not something obvious. Like, I don't know how to see this directly from the definition of coherent cohomology. And so these are the kinds of consequences. This forms a starting point of Hodge theory, where it tells you that really your singular cohomology you should think of as being a Hodge structure. It carries a bunch of extra structure. The first piece of the extra structure is that after you tensor up with C, you have this decomposition into these pieces. And everything you do in algebraic geometry is going to preserve this extra structure. So like morphisms, for example. And so what we are searching for really is a p-adic version of this statement. Is that okay? Great. Right. And so in order to talk about the p-adic version, I need to tell you what the p-adic version of both sides is. The p-adic version of the right-hand side is maybe not so hard to guess because it's defined using algebraic geometry. It makes sense over any field. But the p-adic version of the left-hand side is really, I mean, it's somewhat non-trivial to define. So it's the theory of étale cohomology. And so let me I'm not going to really review the definitions here, but I want to at least do some representative examples. Because we should know what we were talking about. So this theory was conceived in the 60s in the proof of the Weil conjectures. And roughly what happens is that whenever you have a scheme, so say X is a scheme, just for the definitions, it can be anything. And A is a coefficient ring. So there are various choices for A. The ones that are most relevant to these series of talks are going to be one of the following. So it's going to be Z mod n for some non-zero integer n, so a finite ring. Or it will be something like the p-adics, Zp for a prime p, or the fraction field of Zp, so Qp, again for a prime p. P is a prime. And then, given this data, the output of the theory, so this was, I guess, designed by Grothendieck with a lot of help from various people, is a sequence of cohomology groups, which are the étale cohomology groups of X. And I label the coefficients as A. And so I'm not defining them. I'll give you an example of what they look like. But the important thing for what I'm talking about is that these are algebraically defined. I mean, as I stated, this is obvious because the input was a scheme, but I want to emphasize this. So you don't need to know anything about singular cohomology or complex analysis or anything like this to define these groups. And I guess I'm lying slightly, which if you know why I'm lying, then you also know what the fix is. So I want to clarify why I'm lying. Okay, so why is this a useful thing? So the basic theorem, which is Arden's comparison theorem, is that these groups actually compute something we already know about. So if, let's say, X over C is any variety, then what Arden proves is that there is a canonical isomorphism between the étale cohomology of X with A coefficients for one of these A's, and the same thing with singular cohomology. So the right-hand side is defined as you usually do in topology. You compute the cohomology with Z coefficients and tensor up with A. Yeah, question? No. Really? Yeah? It's a true statement. I mean, I guess I defer to Brian, but yes, says Brian. Okay, so what's the upshot of this as far as we are concerned is that since the left-hand side is algebraically defined, so is the right-hand side. And so this gives us certain extra symmetries that act on cohomology that you can't see if you just think about it in terms of singular cohomology. And so let me sort of tell you a concrete consequence of this. So here's an upshot. So say X is defined over Q. So in this case, so what I mean is that there is some x0 defined over Q and X is x0 tensored up with C. And so because of that tensor product, you will have an additional action of the automorphism group of C over Q on étale cohomology just by functoriality, and so it produces an action on the singular cohomology side. And it factors, in fact, it turns out that it factors through the Galois group. So so say X is defined over Q, then with some extra work, so theorem plus epsilon, what you get is that there exists a natural and a highly interesting action of the absolute Galois group of Q on these singular cohomology groups. Or let me just say Xn with A coefficients. And this is the action that we're really going to be interested in. And this is why we use étale cohomology, even though the objects could be defined directly. And so I want to give some examples of this action because I'll carry these examples through the rest of the series. So I think the most important example is going to be that of an elliptic curve. So let's say X equals E is an elliptic curve defined over Q. So in this case, what is this theorem actually? Oh, sorry. What is this theorem actually saying? So we know, I said earlier, oh, sorry. So I want to think of the curve as living over C, but defined over Q. Meaning it's the coefficients of the Weierstrass equation, for example, Y and Q. So you can write E as C mod a lattice, lambda, and I explained earlier how to analyze the singular cohomology in terms of this lattice. And so what does it actually look like? So if you compute H1 of, let's say, Xn with Z mod n coefficients, this is always just going to be the homomorphisms from H lower 1, so the homology with Z mod n coefficients, into Z mod n. The homology is always the abelianization of the fundamental group, which in our case is already abelian because it's lambda. And so this group turns out to be just homomorphisms from lambda into Z mod n. Okay. But it's this, you have this well-known phenomenon that sort of lambda mod n, so this, I can also write this as lambda dual tensored Z mod n. Do I want to do this? No, I don't want to do this. Right. Let me. I should have done something else. It's okay. So the claim is that this is canonically actually identified just with the n-torsion points on the elliptic curve. And this is kind of an easy exercise, which I maybe don't want to explain, but if you use the multiplication by n map. So the multiplication by n on the elliptic curves gives you a finite covering space whose covering group is Z mod n, and such covering spaces are classified by elements of the left-hand side. And if you unwind what that means, that precisely tells you that the n-torsion points of E, which is the kernel of multiplication by n, so it's the covering group that acts on that map, is exactly the homology with Z mod n coefficients. And so in this case, what is the theorem actually saying? The theorem is saying that we have this natural action of this Galois group of Q bar over Q on this En. And so what the theorem is capturing really is that En is defined over Q bar. and not just over C. So the torsion points on your elliptic curve are coefficients in Q bar. And so when you hit them with elements of the Galois group, they get permuted around, so you get an action of GQ on En. And this action is indeed sort of the dual to the one coming from this theorem over here. So, sorry, no one objected, or maybe someone did object and I just didn't look up. But I think I missed a dual somewhere. Thanks. Yeah, so the H lower one is En, and H upper one is En dual. And so this action of GQ on En is exactly the action that Arden's theorem is telling us about. And so we're going to be interested in things like this. And I want to sort of, at the end, pass to the limit over various choices of N. So I just want to introduce the notation. So the Tate module, the p-adic Tate module, say, of your elliptic curve is the inverse limit of EPNs. And the transition maps a multiplication by p. So if you have a p to the n plus 1 torsion point, you multiply it by p, you get a p to the n torsion point. And just by sort of formal nonsense about how inverse limits work, you get a continuous GQ action on the Tate module of E, because you have a continuous action on each of these finite quotients, EPNs, and this is dual to the action to the GQ action on étale cohomology. So on H1 of Xn with ZP coefficients. So the one coming from Arden's theorem. So we're going to be interested in analyzing this action as and in particular understanding something about the right-hand side as a representation of the Galois group. Are there any questions about this example? Please ask questions, because I'm sort of looking at my notes. I'm not looking at you guys, and I don't know what's going on. Okay, and so I guess at this point I want to also introduce, right, so the second example is essentially a similar phenomenon, but for GM, which is maybe easier. But I didn't include it as the first example because it's not compact, so it doesn't quite fit in the framework of smooth projective varieties. But the same analysis as above will show you that H1 of GM analytified with Z mod n coefficients is canonically identified. So here we had the n torsion points on the elliptic curve dualized, and likewise here you'll have the n torsion points on GM dualized. But the n torsion points on GM are just another name for mu n, so you get mu n dualized, the set of all nth roots of unity inside C. And then that's the linear dual. And so the notation is going to be Zp of 1, the Tate twist, which showed up in Peter's talk, is the inverse limit of mu p to the n's over the multiplication by p map. So there's no dual involved. And so and therefore, again, the GQ action on Zp of 1 is related by duality to the GQ action on H1 of Xn with ZP coefficients. And so these Tate twists are going to be showing up a lot in the statement of the Hodge decomposition. So let me just give them a name. So the notation, so this is the first Tate twist of ZP, and in general, for any ZP algebra R, I will just set R of I to be R tensored over ZP with ZP of I, which means you take ZP of 1 and you tensor it with itself I times. So this maybe I should have said this first. So yeah. Sorry, yeah, right. It's the inverse limit over n. What I meant was that the transition maps for multiplication by p. Yeah, thanks. It's the inverse limit over n. And so maybe I should have said this earlier, which is that Zp of 1 is a free Zp module of rank 1. If you fix a compatible system of p power roots of unity, you get a trivialization of Zp of 1, so an isomorphism of Zp of 1 with Zp. And so in particular, it makes sense to tensor it with negative powers of I. So here I is allowed to be negative. And this is just my notation for the Tate twist of R by degree I. And in situations that will show up soon, this R will have a Galois action, and then Zp of 1 has a Galois action, and so the tensor product requires a Galois action. So the whole construction is somehow Galois equivariant. And that will be the Galois action I'm talking about when I have Galois actions in the picture. So note is if GQ acts on R, it also acts on R of I. And it's not really necessary that it's Q over here. It could be any subfield of the complex numbers. Okay, so these are the two examples I want to carry around. I want to mention one more example, which is perhaps the easiest smooth projective variety you can think of, which is not a point, which is P1. So when you do x equals P1, what is this formalism of, oh, sorry, did is that the right thing to do? I think so. Okay, yeah, so if x equals P1, how do you compute its étale cohomology or its singular cohomology? The way to compute singular cohomology is easy. P1 is covered by 2 copies of A1, so that gives you some kind of Meyer-Vietoro sequence computing the cohomology of P1 in terms of the cohomology of A1, cohomology of A1, and then cohomology of the intersection, which is a GM. And then A1s are kind of boring, so you just end up getting an isomorphism between H1 of GM and H2 of P1. And those computations involving things like Meyer-Vietoro sequences and so on are completely sort of, they're completely natural, so they go through in exactly the same way on the étale side. So if you think about what that means, it means if you look at H2 of P1, let's say analytified, with Q coefficients, this is isomorphic as a GQ module to H1 of GM analytified with Q coefficients, which we just said was, so I said with Z mod n coefficient, with ZP coefficients I was getting ZP of -1, and so with Q coefficients I get Q of -1. Or maybe I should have put it, sorry, let me do QP. Thanks. And this is all happening as GQ modules. And so the second cohomology of P1 with QP coefficients is just a one-dimensional vector space because topologically it's just a sphere, but it has an interesting Galois action, and it's the Galois action on the p-power roots of unity. And this is actually a general phenomenon. So more generally, if X is smooth projective of dimension D, then the top cohomology is always given by a similar formula. So H2 of Xn, let's say with QP coefficients, is always QP with the Tate twist, and the Tate twist is given by the dimension D as Galois modules. And so the point I'm trying to make is that these Tate twists are naturally showing up when you think about the étale cohomology of smooth projective varieties. Okay, so that was my very brief overview of what étale cohomology is and the main examples I care about. What I want to do, the reason I was doing that is I want to tell you about the Hodge-Tate decomposition. So let me actually formulate what the statements are. So my understanding is that, so the story of the Hodge-Tate decomposition begins in this paper of Tate on p-divisible groups, which Peter mentioned. And that's also a paper where a lot of the modern objects in p-adic Hodge theory originated. And so for the grad students, if you haven't looked at this paper, I really recommend studying it. It's fun. So the Hodge-Tate decomposition is supposed to be a p-adic analog of the Hodge decomposition. So let us introduce the notation. So you fix a prime p. My field K is going to be a finite extension of QP. And I will also fix an algebraic closure of K. So I'll fix K sitting inside K bar, and then K bar might not be p-adically complete, so you have to complete it. And that object will be called CP. And so on K bar, you have a Galois action of GK, which is the Galois group of K bar over K. And just by continuity of how Galois acts, it also ends up acting on CP. So CP is naturally a GK module, and this GK module is going to play a crucial role. Oh, okay. So that's the setup, and what's the statement? The statement is very analogous to the Hodge decomposition. So the theorem, which is the Hodge-Tate decomposition, says the following. So say x over k is a smooth projective variety, then there exists a natural, but in this case somehow the naturality can be quantified in a much more precise way. So I'll say it's actually Galois equivariant. So GK equivariant isomorphism between Hn of x k bar, so it's a tau cohomology with QP coefficients, and then on the right hand side you're going to have some direct sum I plus j equals n hi of x omega j of x over k. Except it's not quite so simple, because life can't be so simple. So what you have to do is you have to use this Galois module CP that I mentioned earlier. So this actually, in fact, already happened over the complex numbers, right? Like on the left-hand side of the Hodge decomposition, we had singular cohomology with Q coefficients, but then we had to extend scalars to see the isomorphism with de Rham cohomology. And that isomorphism could not be defined over a smaller field because of things like periods showing up in the isomorphism. So something similar happens here. So you have to go up to CP on the left-hand side, and then also on the right-hand side. And then, right, the important thing is a Tate twist. So there's a Tate twist of minus j showing up on the right-hand side in the jth summand. Okay, so let me maybe say where the Galois action is coming from. So on the left-hand side, here I have xk bar. So it's just the base change of x to k bar. So Galois acts on k bar, and therefore it acts on xk bar. And that's the Galois action on this factor. There's a natural Galois action on CP, as I mentioned over here, so you have a tensor product action on the left-hand side. And then on the right-hand side, this factor is defined over K. It's just the coherent cohomology over K. It has no action, so it's a trivial action. But CP of minus J has a Galois action, coming from what I was saying earlier about Tate twists and tensoring them with rings with the Galois action. And so this is GK equivariant, where GK acts in the natural way on both sides. So you don't have to do anything funny with the action. Okay, and so in my notes I have something about the history of this theorem, but maybe I will not talk about the history here. We'll sort of see finer versions of this theorem later in the talk, and those are the ones we'll actually end up discussing. But I should say that I think the first complete proof of this is due to Faltings in his first paper on p-adic Hodge theory. The special case of abelian varieties was done earlier by a combination of work of Tate, Reynaud, and Fontaine. Okay, so the goal of this lecture series is to explain what this theorem, how to prove this theorem. But the goal of today is to explain why this theorem is useful for you. So what are the kinds of consequences you can extract out of it? And so to use this, I mean, if you want to use this theorem and you want to use the fact that the Galois group is rich, you need some way of saying that the different factors that are showing up on the right-hand side are somehow independent from each other. They don't talk to each other. And that's actually true. So that was the theorem of Tate in this paper on p-divisible groups. So what he proved is that if you fix integers I and j, I not equal to j, then there are no harms between the different Tate twists, and then there are no extensions between them either. So harms, there are no Galois equivariant homomorphisms from CP of I to CP of j. And then there are also no Galois equivariant extensions between CP of I and CP of j. And so what this is saying is that these twists somehow don't talk to each other. So if you have a short exact sequence where the source term has a different Tate twist from the quotient term, then you can just split it off completely canonically. You can choose any splitting that you want, and as long as it's Galois equivariant, it will, which it has to be because the x1 vanishes, it will be canonical because the harms vanish. And so it really is saying that in a very strong sense, these summands cannot interact with each other. And I'll explain the use of that in a second. Okay, so let's first see some examples. So let's see what this theorem is saying in the case of x equals p1 and n equals 2, I guess. So you're trying to compare these two cohomology theories. I already explained how to compute the left-hand side. So H2 of x k bar with QP coefficients is supposed to be isomorphic to the right-hand side, which has 3 summands. So I will just, so it's H2 of XOX tensored with CP. Because so the way to remember this is that the degree of the differentials is the degree of the Tate twist. So if you have an omega j, it comes with a twist of minus j. So omega 0 comes with no twist. So you have this summand, and then you have H11 summand, which comes with a twist of minus 1. And then you have this third summand, which is H naught of x, omega 2 of x, which comes with a twist of minus 2. Sorry. Well, it's not so important because it's 0. Right, but I'll try to write bigger. Tensored with CP on the left side. Thank you. Okay, so let's actually just see what these objects are. So the left-hand side, it's H2 of P1 with QP coefficients, which I said was QP of minus 1. And then you're tensoring it up with CP. So you have CP of minus 1. We already know what the coherent cohomology of P1 is. But if you didn't know it, you could use this theorem to figure it out. Okay, that was completely stupid. Okay, so this guy is 0 because P1 has dimension 1 and coherent cohomology vanishes above the dimension. This one is 0 because omega 2 is 0 as a sheaf because it's a smooth curve, so there is no 2 forms on it. And this guy is H1 omega 1, which you can easily compute to be one-dimensional vector space. So it's H1 of the canonical, which is always one-dimensional on a curve. And so here again, you get a CP of minus 1. But so in this case, this theorem is capturing the information that these two groups vanish. And this one is one-dimensional, which is not completely tautological, but kind of easy to see. The more interesting example, which is the one we'll sort of spend a lot of time on, is elliptic curves. And so the degree of cohomology to stare at over here is 1. So let's again try to just write down everything. So here you have H1 of xk bar with QP coefficients tensored up to CP. And here I only have 2 summands, so I can write a little bigger. So it's H1 of XOX tensor CP, direct sum H0 of x omega 1x tensor CP of minus 1. And so we computed what this side was earlier. This was the Tate module of your elliptic curve dualized, and then now we have to tensor up. So it's TP of E dual tensor CP. H1 of an elliptic curve with coefficients in the structure sheaf is one-dimensional, which you can compute using Riemann-Roch. So this guy is CP. And H0 of omega 1 in an elliptic curve is also one-dimensional. So this guy is a one-dimensional vector space. So these are tensor products over K. And you tensor it up with CP of minus 1. So CP of minus 1. And so what you end up getting in this case is this decomposition of the Tate module tensored up with CP into these 2 summands. One is CP and one is CP of minus 1. So what this theorem is saying is that these representations, like the Galois action on the Tate module, which are very interesting, somehow completely break apart when you go up to CP. They break up into copies of things you can understand more easily, namely these Tate twists. And that's really how the theorem is used in practice. And so, yeah. So let me actually write. I wanted to also say how you can write these things slightly more canonically, which maybe might jibe with other things you've seen in the literature. So if you ignore this middle isomorphism, which is totally non-canonical, if I go all the way over here, how do you think about H1 of XOX in a canonical way? Well, H1 of XOX for any smooth projected variety X is always the tangent space of the dual abelian variety. So this is the Lie algebra, if you like, of the dual abelian variety, which is the dual elliptic curve. So this is the Lie algebra of E dual tensored with CP. Hopefully I got, yeah, okay. And then this guy is 1 forms on your elliptic curve. So 1 forms on any group are the same as sort of cotangent vectors based at the origin. Cotangent vectors based at the origin are dual to tangent vectors based at the origin, and tangent vectors at the origin are the Lie algebra. So this is the Lie algebra of E dualized, tensored with CP of minus 1. And so this is maybe a form in which this result is somewhat more appealing visually to look at. It's sort of describing how to decompose this kind of topological object, which is the Tate module, in terms of sort of more differential information attached to your group, namely the Lie algebra of the group and its dual. Okay, so I promised to explain how to actually use this Hodge state decomposition to do something. And there are lots of ways it ends up getting used in number theory, but I want to explain one of my favorite applications, which is sort of a more geometric nature. So I'm going to just, for the set of, don't need to do this. Oh, no. So here's a corollary of the Hodge state decomposition, which is that if you have x over k, which is smooth and proper, or smooth and projective, because that's what I said earlier, then you can recover these coherent cohomology groups, hi of x, omega j of x over k, purely from the étale cohomology. Okay. So if you just stare at this formula, it's not completely clear how to recover this, because on the right-hand side, we said earlier that the twists don't interact. So you know that you can isolate the summand hi of omega j tensored up with Cp of minus j. But how do you sort of undo that tensoring? Well, you undo it by taking a Galois invariance. So if you just go through what this theorem plus this theorem combined to tell you, you end up getting the following formula. So it's hi plus j of xk bar with qp coefficients tensored up with Cp, and then I think a Tate twist of plus j, and then the gk invariance. And so what this is saying is that you can recover sort of differential information attached to x, namely things like one forms in their global sections from this topological information attached to x, namely this étale cohomology with its Galois action. And this is something that's sort of very specific to the arithmetic setting. So there's this analogy between local fields where you can think of sort of QP as being an arithmetic version of a closed unit disk over the complex numbers. And there's a similar kind of theorem over the complex numbers, but it's not strong enough to recover the coherent side from the étale side or the topological side. So it's really a strength of the fact that it's a consequence of the fact that this group is sort of huge, and as a result, representations of that group are highly interesting invariants. And so the explicit way this was used, I'll just record in this remark. So Ito used this corollary to reprove the following theorem, which has nothing to do with anything p-adic. So the theorem is as follows. So you say x and y are Calabi-Yau varieties over the complex numbers. So there are smooth projective varieties and there are Calabi-Yau. So the canonical is trivial. And you know that x is birationally isomorphic to y. Then the theorem is that in this case, the Hodge numbers coincide. So hij of x is equal to hij of y. So this is just the dimension of hi of x omega j. Hj omega I. Yeah, so I mean, this was a conjecture. I actually am not sure who conjectured this first, but Badarev proved that the Betty numbers have to be the same in this setting by a point counting argument. And then using Badarev's ideas, Kontsevich came up with this theory of motivic integration, which lifts Badarev's argument to prove the equality of Hodge numbers. But then Ito realized that once you have the point counting argument, you actually get an equality of zeta functions. And once you have an equality of zeta functions, you get an equality of Galois representations up to semi-simplification. And that's good enough because of this formula over here to actually recover the Hodge numbers directly. So you can somehow completely forget about motivic integration in order to prove this theorem, which as an arithmetic geometer I like. Okay, and then I want to make one more remark before actually saying something about how we go about proving this. So the remark is that in the statement of the Hodge state decomposition, I restricted to the case of smooth projective varieties. You can wonder what happens if you drop the assumptions that x is smooth or projective. And it turns out there's actually a very good theorem even in the general case. So there exists a good variant for general x. I don't want to formulate it here because that would require introducing a little bit of terminology from mixed Hodge theory. But for people that know mixed Hodge theory, essentially you replace hi of omega j on the right-hand side with Gur j of Delane's Hodge filtration on de Rham cohomology. And then the same formula is true. And this is something that is related to one of the projects that I wrote up in my lecture notes. Okay. What time did I start? What? I have 10 minutes. Great. Okay, so what I want to talk about now is how we're going to actually go about proving this theorem or some approximation to this theorem in this lecture series. And the strategy is to first prove a slightly weaker statement. But, well, it's a somewhat orthogonal statement. It's weaker in some ways and stronger in some other ways. And then at the end, sort of say why it implies the Hodge state decomposition. And so this thing that we'll actually concentrate on is not the Hodge state decomposition, but rather the Hodge state spectral sequence. And so this is due to Peter. And we will use perfectoid spaces to actually construct the spectral sequence. And so what does it actually look like? So we'll use the theory of perfectoid spaces to prove the following statement, which I'll call the Hodge state spectral sequence, HTSS for out of laziness, I guess. So the setup here is slightly different. Instead of, since in the perfectoid theory we are told that we should forget about every finite type object and work with these really large objects, let's work over a large field. So C over QP is complete and algebraically closed, non-Archimedean extension of QP. So you can take it to be CP, the field from before, but it doesn't have to be. It can be much larger. And then X, the geometric object that we're going to think about, is you can take it to be a smooth projective variety, but actually the theory works best if you put yourself in this context of adic spaces. So this is going to be a proper, smooth, rigid analytic space. So it can be algebraic, but the theory doesn't care that it is algebraic. And then the theorem is that in this case there is not quite a decomposition anymore, but there is a spectral sequence in terms of very similar looking objects. So there exists an E2 spectral sequence. Which goes like so. So it's E2ij, goes from hi of x, omega j of x over c. And now since I'm already working over c, I don't need to sort of do this extra tensor product with c. So I can just say, put a Tate twist over here. And this converges to hi plus j of x qp tensor up at c. So the right-hand side here is a Tal cohomology as defined by Huber for adic spaces. And so I'm looking at Huber's Tal cohomology, tensoring it up with c, and saying that there is a spectral sequence which is computing this object in terms of differential forms with Tate twists. And so as an upshot of this, whenever you have a spectral sequence, in particular, you get a filtration of the thing it's converging to. So you get a filtration on the Tal cohomology tensored up with C. And that filtration is called the Hodge state filtration. So you get the Hodge state filtration. On Hn of x qp tensor C. And we're going to spend some time sort of building up to where the spectral sequence comes from. But let me just, I want to spend my remaining time, my 5 minutes, to make a few remarks about this spectral sequence. So I'll save perhaps the most interesting one for, I won't make it first. The first statement is that, first of all, what does this mean that I have a Tate twist over here? If I'm already working over C, there is no Galois action. So a priori, this is kind of a meaningless thing to do. But the spectral sequence is completely canonical. So if X came from something that was defined over a smaller field, then this object would have inherited a Galois action. And then the assertion is that the spectral sequence is equivariant for the Galois action. And so the Hodge state spectral sequence is functorial. By which I mean what I was saying. And so a consequence of this is that if X is defined over K, where K is from before, where K over QP is finite, then everything in sight has a Galois action, and the Hodge state spectral sequence is equivariant for the Galois action. But we had this theorem of Tate that was telling us that the different pieces, the different Tate twists cannot interact with each other. And moreover, there can't be any interesting extensions between them either. So if you think about what this means, it tells you that the spectral sequence, not only does it degenerates in sort of in a unique fashion. And so what it really says is that then if you use Tate's theorem, you get a Hodge-Tate decomposition. So you recover the Hodge-Tate decomposition as I formulated it earlier. But what we gained is that now it also works for proper smooth rigid analytic spaces instead of just proper smooth algebraic varieties. So you're extending the realm of the Hodge-Tate theory into the analytic setup. And in some sense, this is sort of similar to something that happens over the complex numbers. With the complex numbers, the Hodge decomposition is true not only for smooth projective varieties, but really for compact Kähler manifolds. And so here we are saying we don't need any analog of the Kähler assumption either. It just works for any proper smooth rigid space. And as Jacob was explaining to me, the Kähler assumption is kind of analogous to having a good metric. And if you think about it that way, the analogous thing here should be that a proper smooth rigid space has a formal model, because the formal model gives you a metric. And I guess this is always true. So you don't need any Kähler-like assumption because it's always satisfied. And so this actually answers a question that Tate asked in his original paper, whether the Hodge-Tate decomposition exists for analytic objects. The second remark I want to make is that the spectral sequence always degenerates. So this relies on work of Conrad and Gaber on approximating rigid spaces. But it does degenerate, but since you don't have a Galois action anymore, you can't say that it canonically degenerates. And so what you can say is that you get a Hodge-Tate decomposition. There is some Hodge-Tate decomposition, but you can't sort of choose it in a nice way. So it always degenerates, but not canonically so. And so let me just end by saying what a concrete consequence of this phrase, not canonically so, over here. So example, say x over, say x equals E is an elliptic curve. Then the Hodge-Tate spectral sequence, if you sort of look at the low degree terms of the Hodge-Tate spectral sequence, it gives you an exact sequence like this. So you have H1 of XOX with no Tate twist sitting inside H1 of XQP, tensor up with CP, and then the co-kernel looks like H0 omega 1 with a Tate twist of -1, and then a 0 over here. So if you get a low degree short exact sequence like this. But there are two things to point out over here for this sequence. So first is that it sort of goes the wrong way. Maps go the wrong way. By which I mean if you did the analogous low degree exact sequence over the complex numbers, you would have one forms which map to cohomology, and then cohomology has a map to the cohomology of the structure sheaf. As we saw earlier, you can take a one form and you get a cohomology clutch just by looking at the integration pairing. And so here somehow the maps are going in the wrong way, where the one forms are actually a quotient of your topological object rather than the sub. And this is kind of a common phenomenon in this arithmetic setting. So a much more classical version of this is the conjugate spectral sequence in the de Rham cohomology of varieties in Kirsig P, which I think will be maybe explored in the problem sets. And then the second remark is that we cannot choose a splitting that varies in a family. So you can imagine that you have not just one elliptic curve, but a whole family of them. And then for each point, you can sort of choose a section like this. And then you can ask if you can actually choose this section in some canonical way, so it extends across the family. And this actually can't happen. So this subspace really moves inside this vector space over here. And this kind of infinitesimal, this invariant that sort of measures the position of this subspace inside this vector space is measured by the Hodge-Tate period map, which I think will be showing up in Anna's lectures, which is why I wanted to mention it. But okay, I think I'm going to stop here for today.
Is there any hope, so I don't see any, but maybe an expert, is there any hope that one will someday be able to apply p-adic methods to give an algebraic proof of symmetry?
I don't have any ideas about how to do this. And I don't even know if there's a plausible hope. I'm willing to ask this question to the audience, but Yeah, but is there any hope of giving an algebraic proof of hard Lefschetz? Maybe you find out on Thursday in your last talk.
So my comment was just that it follows from hard Lefschetz and the Hodge state decomposition. And didn't the Lehm prove hard Lefschetz algebraically in Veil 2 or so?
I guess so.
Oh, here we are.
There you go.
Anybody want to ask if this leads to a proof of the Riemann hypothesis?
So perhaps you could remark why the Hodge state spectral sequence goes in the opposite way to the Hodge spectral sequence, and it's E2, not, I mean, it's more like the conjugate spectral sequence.
It is like the conjugate spectral sequence. Well, I'm not sure what exactly I can say about it, which is except that one of the projects of my evening groups is to actually prove the statement that you made, that the two are specializations of the same phenomenon. So if you work integrally, you can define some integral Hodge state spectral sequence, and then the hope is that when you reduce it mod p, it coincides with the conjugate spectral sequence, and when you rationalize, it coincides with the one I just described here. But maybe an easier answer to your question is that it's really coming from describing Étale cohomology as the cohomology of a coherent sheaf, or a complex of coherent sheaves, of O modules, which is why somehow it's an E2 thing, because it's a coherent phenomenon. Whereas if the Hodge to de Rham spectral sequence comes from describing Étale cohomology, a singular cohomology in terms of the de Rham complex, which is not O linear. And so there you're using the stupid filtration on the complex, whereas here you use the canonical one.
So Fontaine's theory and Faulting's result gives filtration anyway on the Étale cohomology, right?
In the algebraic case.
Right.
Yeah.
And how does that compare with this filtration coming from the Hodge state
I
spectrum?
think it's the same.
Compatible?
I think so. I would ask Peter, but I think the construction is the same. Yeah.
So in the complex case, we have this like very nice interpretation in terms of integration against a differential form that you showed in the case of an elliptic curve. Is there some nice interpretation in the p-adic case in terms of some sort of integration, like maybe Coleman integration or something like that, of this Hodge-Tate decomposition?
I'm not the best person to ask about this. I think the answer is yes in some cases, but I would probably not be the best person to ask about this. You should just ask every question there. Do you get sort of, it goes beyond the, it works in the good reduction case? Right, so I thought the furthest you could get with this method is when the special fiber is highly degenerate, and then you can produce something.
Yeah, sorry, I'm also not the best person to ask, but I wanted to remark that I think the best statement that I'm aware of in this respect is in Colmes's asterisk volume on, I don't know what it's called, but where he explains how to get something, like I think even the beta-Ram comparison using something like integration. But it's in the one-dimensional case, I mean for curves or beam varieties. And okay.
Okay, let's thank Bhargav again.